So far, we've talked about a lot of definitions and a lot of procedures. In this lecture, we're going to put all of this together into a complete procedure for solving systems of linear equations using a method called Gaussian elimination with backward substitution. So to demonstrate the algorithm, we'll look at an example of each of the three possible outcomes. We'll look at the independent case, where there's a single point for a solution. We'll look at an example of the dependent case, where there are multiple solutions, and then finally the inconsistent case where there are no solutions. Now the basic algorithm has three parts. First, convert the system of equations to an augmented matrix. Then use the row reduction algorithm to put the matrix into a row echelon form. This step is also often referred to as Gaussian elimination. Finally, we'll use what's called backward substitution to get the final results from that echelon matrix. So before we do that, I want to talk about a notation that we use to indicate these different elementary row operations. Right? Talking about them can be a little messy sometimes. This notation is going to help us to do that in a really kind of compact way. So what I'm going to do is I'm going to label each row R1 through Rn. Then this is the notation I'm going to use for the elementary operations. If I want to switch row I and row j, I'm going to put Ri and Rj with this double arrow in between. This notation is saying I'm going to take row I, multiply all of its values by A, and put those new values into row I, replacing the values that were there before. And finally, this is our third elementary operation. This is saying I'm going to take the elements from row I, the elements from row j, add them together, column-wise, and I'm going to put the results back into row I. Now, there is one other notation. This isn't really an elementary operation because we've got two of them together here. But the row reduction algorithm, for a lot of the steps, we multiply a row by a number, then add it to another number. Right? And that's what I'm trying to notate here. I'm taking row j, multiplying all of its values by A, adding those values individually to the elements in row I, and replacing row I with those new values. Okay, so with that in mind, let's look at some examples. So I've got a system of equations here for us to solve, and this is going to be the independent case, or we're going to get a single point for our final solution. So my first step is going to be to take this and turn it into the corresponding augmented matrix. And I'm going to focus first on the first column. That's going to be our first pivot column, with the 2 and what will ultimately end up being the pivot position, right? The A11 position. So my goal here is to eliminate every number under that A11 position in that first column. By eliminate, I mean perform some row operations that turn the 1 and the 4 both into zeros. Now, if you're running an algorithm to do this, the computer doesn't care about messy arithmetic. If we're doing this by hand, then there are some choices we can make that will hopefully make the calculations simpler. One of those is moving an entry whose value in the pivot column is 1 into the pivot position. Because if we do that, all of our multipliers are going to end up being integers. Right? So to make that switch, I'm going to switch row 2 and row 1. So that makes my matrix look like this. Now, I'm ready to start doing the row reduction process. So my first goal is going to be to eliminate this 2. Right? And to do that, I'm going to define a multiplier. Right? That's going to be the A from my notation on the previous slide. That multiplier is going to be A21, that's the 2, divided by A11, that's the number in the upcoming pivot position. If I do that, we get 2 for our multiplier. So what I'm going to do to eliminate that 2 is this operation. I'm going to multiply everything in row 1 by 2, subtract those values from the values in row 2, and put those numbers into row 2. So this is where we end up. Right, looking just at the first column, 2 times 1 is 2. I subtracted 2 from the original 2, and yeah, I got 0. Good, that was the number I was aiming for. And I did that to every other number in the row. So I multiplied negative 5 times 2, subtracted that from 4. 4 minus 10 gave me 14. Minus 1 minus 2 gave me negative 3. And 1 minus 2 gave me negative 1. That's my new row. Okay, so now I'm going to do it again. And now I'm going to do the process again, but this time I'm targeting this 4 to be the number I'm going to eliminate. And my multiplier here is going to be a 3, 1, that's the 4, divided by a 1, 1 again. So that gives me 4 for my result. And that's the row operation I'm going to execute here. So I'm going to multiply row 1's values by 4, subtract those values from R3, and that gives me the new R3 values. Okay, so if we implement that, and you're welcome to check my arithmetic here, just looking at the first column, 1 times 4 is 4. I subtracted that from the 4 in the third row, and yeah, good, I got 0. For the second column, negative 5 times 4 was negative 20. 14 minus, what did I say? Excuse me, negative 1. Negative 1 minus negative 20 gives me 19, and so on across that row. Okay, so now we're done with the first column, right? Every row under the pivot column is a 0. We're good to move on to the second row. Okay, now I want to eliminate everything under the 2, 2 position, and there's only one number. I got to get rid of that 19, and now here our choice back up at the first operation is going to come back to bite us a little bit. Now my multiplier is going to be this somewhat unpleasant fraction. It's A32 divided by A22, the number in the pivot column, right? That's the 14, the pivot position. And yeah, okay, so I don't know if this would have been easier if we had left the original rows alone. This is kind of one of the challenges of this algorithm. There's a lot of multiplications, a lot of divisions, a lot of additions and subtractions, and it's hard to predict up front what a given choice is going to, what the impact is going to have 2, 3, 10, 20 steps down the cycle. So we made our choice. We're stuck with the 19/14. This is the row operation I'm going to execute. I'm going to multiply row 2's values by negative 19/14 and add those to R3. If we do that, and again, you're welcome to pause and check my arithmetic. It's good practice for you, right, to get a handle on these steps. We get this matrix, and at this point, we're done with the elimination process. This matrix is a reduced row echelon matrix. So we're good to move on to the next step. Excuse me, I misspoke there. This is an echelon form of the matrix, right? Not a reduced row echelon form. So you think about that for a second. All of the numbers in the pivot positions aren't ones. So this is not a reduced row echelon form. It's just an echelon form. So now we're moving on to the backward substitution phase of this Gaussian elimination with backward substitution algorithm. And my first step is going to be to take this echelon form of the matrix and convert it back to a system of equations. Right? So I'm going to get x minus 5y plus z equals 1 from the first row, 14y minus 3z equals negative 1 from the second row, and 29/14 z equals 145/14 from the third row. So notice that third row only has one variable. Right, so this is why this is called backward substitution. I'm actually going to start with the last variable, or the last row of the matrix, and work my way backwards up to the top, where we'll get, at the end of the process, the value of the first variable. So solving that equation is pretty straightforward. We multiply both sides by 14, divide both sides by 29, and we get z equals 5. So despite having to deal with having those messy fractions turn up, it came out nice in the very end here. Now I'm going to continue with the backward substitution. I'm going to take that 5, I'm going to substitute it into the next equation up, solve that equation for y, and we get y equals 1. And now I'll do it one more time. Go back up to the top equation. I'm going to put 5 in for z, 1 in for y. We solve that equation, we get x equals 1. And there's our complete solution. 1, 1, 5. Okay, so how about the inconsistent case? Well, I'm going to follow the same procedure. I'm going to take my equations, I'm going to convert them to an augmented matrix, and I'm going to go through the row reduction algorithm. First, I'm going to target that 1. Right? To do that, my multiplier is going to be A21 divided by A11. That's 1/2. So if I do this row operation, R2 minus 1/2 R1, that's going to eliminate that 1, and that gives me this equation. Now at this point, I'm a little concerned. I'm looking ahead. I'm going to need to get a non-zero pivot value in that second column, and that 0 was a little worrisome. But you cross your fingers. If we get a non-zero value in the 3, 2 position, where the 2 is, and the first 2 in the last row, yeah, then I'm okay. Then I'll just switch rows 2 and 3, and we can carry on. But let's see what happens. Right? My next step is going to be to target that 1. My multiplier is going to be A31 divided by A11. That's 1/2. So this is the row operation I'm going to execute. I'm going to do R3 minus 1/2 R1, moving that into R3, and that gives me this. And yeah, now I'm in trouble. Right now I'm in trouble. I do not have a pivot available in that second row. And that's telling me this is going to be the inconsistent case where there are no solutions. Right? And to see this, try to do the backward substitution step. Right? If I take the middle row, convert it back to an equation, I get 3/2 z equals 1/2. Solve that, we get z equals 3. But now do it again with a third row. That gives me 5/2 z equals 25/2. We saw that and we get a completely different value for z. Obviously, z can't have 2 individual distinct values here, so that's a big red flag. This is an inconsistent situation where there are no solutions. Okay, so how about the independent case? You notice that this is a little different. Right? I only have 2 equations here. That's a big red flag that there is not going to be a single solution. If you just visualize this, each of those 2 equations represents a plane in R3, in 3-dimensional space. The intersection of 2 planes is never, ever going to be a single point. Either they're going to be parallel and they don't intersect at all, or they intersect in a line. Okay, so we really kind of know right up front that single solution case is off the table. But let's go through our process. I'm going to get the augmented matrix, and I'm targeting the 3 in the first column. My multiplier will be 3/1 divided by 3. That's 3. Good. It's an integer. Came out nice. So this is the row operation I'm going to execute. R2 minus 3R1, and I'm going to copy those values back into R2. Okay, that gives me this matrix. Now at this point, the elimination phase is done. That is an echelon form of this matrix. Right, so what I'm going to do is I'm looking at this and I'm saying, okay, we have 2 pivot columns. Right, row 1 and column 1 and column 2 are pivot columns. That means those are my base variables. Column 3 is not a pivot column, which means the third variable, the z variable, that's going to be a free variable. That variable can take on any value you want to substitute in for it. Then what I'm going to do is I'm going to take the other 2 equations. Right, let's start with the second one. If I convert that second line back into an equation, I get negative 2y plus 4z equals negative 2. And I'm going to solve that for z. Move the z over, divide everybody by negative 2. And I get y equals 2z plus 1. Okay, that's my formula for the acceptable y values. Right? Values that will represent a solution to both of these equations. Now finally, I'm going to do this one more time. I'm going to take the first row, convert that back into an equation, x plus 4y minus z equals 1. I'm going to substitute 2z plus 1 for y, right? Because my ultimate goal here is to have formulas for the base variables in terms of the free variable. So I want to have a formula for y in terms of z, which I did, and now I'm going to get a formula for x in terms of z. That's negative z minus 3, and now I have my solutions. And now I have my solutions. My solutions are negative 7z minus 3, comma 2z plus 1, comma z. Right? At any point that has that form will be a solution to both of those equations for any value of z. And if you look at these equations, right, and think back to the geometry, I said there's two possibilities, right? No solutions or a line. Well, yeah, these are describing a line, right? Z is increasing linearly, y is a linear function of z, and x is a linear function of z. So yeah, that is describing a line in R3, in three-dimensional space. Okay, so I have links to two things here. If you're interested in the computer design, the software, the algorithm side, one of these links goes to our numerical analysis class, to one of the lectures from that class, where we really formally define this algorithm in terms of pseudocode. Something that you can turn around and implement in the programming language of your choice. So if you're interested in that thing and that kind of thing, you click on that link and you'll find some great information there. The next lecture in the series is one of the theoretical ones. We're going to take up the question of existence and uniqueness for these echelon matrices. If you're not interested in the theoretical side, that's perfectly fine. You're welcome to jump ahead to the next lecture after that, where we're going to continue this conversation about solving systems and linear equations by looking at a special kind of matrix called a vector.